The second one is interesting. A coil of self-inductance L is connected in series with a bulb B and an AC source. Brightness of the bulb decreases when. There are four options. This question appeared in the past MCQ examination. Frequency of the AC source is decreased, number of turns in the coil is reduced, a capacitance of reactance Xc equal to XL is included in the same circuit, and iron rod is inserted in the coil. The only simple analysis. A coil of self-inductance L is connected in series with a bulb B and an AC source. B bulb, it supports a resistance. So you have a RL circuit, that is resistance and inductor. Brightness of the bulb depends on what? Brightness of the bulb decreases, what happens to the current value? We'll address it very systematically. Let me have an analysis. When a bulb of resistance R is connected in series with a coil of self-inductance L, the current in the circuit is given by mathematically the current formula is EMF divided by the opposition. The net opposition is given by impedance. The impedance is nothing but the sum of the oppositions offered by bulb plus inductor. Inductor opposition is XL, whereas bulb opposition is R. So it is actually EMF upon Z. Z is given by under root R square plus XL square. XL square is omega L. Since XL is omega L, this value is omega square L square for an AC source. It is called RL circuit. Means bulb is act as opposition R and L is an inductance. We know that L is given by mathematically beautiful formula. L is nothing but mu 0 mu R n square A upon, of course, L. So this is directly proportional to, you have a symbol mu R. This is called permeability of a material. So out of the four choices, the question first one ruled out. Second one, of course, it is number of turns, but we give up. And third one, not at all accepted. The fourth option, an iron rod is inserted in the coil. So mu R supports the iron rod. The permeability of iron rod is very high. When iron rod is inserted, L increases. So in this formula, current is given by EMF on under root L square. L increases as square, it is squared. The denominator becomes very, very big quantity. When the denominator big quantity, the whole ratio becomes very small. When the iron rod is inserted, L increases. Of course, L increases because mu R increases. L increases. If L increases, the denominator whole term increases. Hence, the ratio, that is EMF upon impedance, impedance becomes large. Then naturally the current becomes less. Therefore, current I decreases. This is the standard answer. The answer is an iron rod is inserted in the coil. The same explanation is done in another way, mathematical form. Over. Then the situation is as shown in the figure, like you have an inductor, you have a bulb. Let me read it. You will appreciate it. As the iron rod is inserted, the magnetic field inside the coil magnetizes the iron. Do remember, magnetic field inside the coil, because the coil will act as a source of magnetic field. It magnetizes the iron, increasing the magnetic field inside. Hence, the inductance of a coil increases, L increases. Consequently, the inductive reactance, that is XL, of the coil increases. As a result, a larger fraction of the applied AC voltage appears across the inductor. As a result, larger fraction of the applied AC voltage appears across the inductor, leaving less voltage across the bulb. Therefore, the brightness of the bulb, light bulb, decreases. Here, yes, the formula is voltage across the inductor becomes very large and voltage across the bulb becomes very less. Therefore, the brightness of the bulb decreases. So this numerical will address what exactly is the parameters current to resistors. What are the situations I need to correlate? The new opposition offered by the total impedance, which is nothing but under root R square plus Xc square. So I need to write it the whole expression mathematically. So it looks like the next thing. So the current in the circuit is I equal to V by Z. It's a RC circuit. The voltage is V, that is voltage, and Z alternating voltage is V, and Z is the total opposition. Total opposition, as I said, is written as under root R square plus Xc square. Xc means 1 upon 2 pi Fc, that is omega C. So mathematically, when you simplify it, this 2 pi square, it becomes 4 pi square Fc. It is 4 pi square F square C square. R square is already available. The denominator comes out of the root. It comes in the numerator. It is 2 pi Fc into V. I equal to V, and this is a value. Now you need a formula, that is voltage across VA and VB. Look at this formula. Voltage drop across the capacitor. So whenever I had a voltage drop across the capacitor, Ohm's law comes into picture. That is I into R. R means opposition offered by capacitor. Opposition offered by capacitor is 2 pi Fc. V is missing up. This V is missing. Don't worry in the equation. Divided by under root. This nullifies each other. Left with Vc equal to V times V divided by 1 upon under root 4 pi square. Everything is available. This inside the bracket parameter 4 pi square F square C square R resembles my dielectric parameter, that is dielectric constant. So this I will write in terms of dielectric constant of a capacitor. When you insert it, so naturally the things will. Now when mica is introduced, we all know capacitance increases, voltage across capacitor decreases, hence voltage across A and voltage across B are related in this fashion. VA is greater than VB. What is VA is greater? Because K increases, K means your voltage across capacitor. When dielectric is introduced, capacitance increases, but voltage decreases. Voltage decreases means voltage across a capacitor when mica is filled, it is VB, VB decreases and VA increases. Hence, the relation is, of course, it is VA greater than VB. An AC voltage is applied to a resistance R and an inductor L in series, that is called RL circuit. If R and the inductive reactance stands for XL, are both equal to 3 ohm, R equal to 3 ohm, XL equal to 3 ohm, the phase difference between the applied voltage and the current in the circuit is. There are 4 choices how to address it. We know that in case of inductor, there is a phase difference. If the source is applied to resistor, there is no phase difference. What is the phase difference in case of voltage and current? In case of RL circuit, let me address it. Tan phi stands for the phase angle. Phase angle is given by, I hope I have discussed at length. It is a ratio of opposition offered by the inductor to the opposition offered by L. Actually, it is XC minus XL or XL minus XC upon R. So since it is RL circuit, there is no C contribution, that is XC. So it is XL upon R. XL is written as omega L upon R. And the formula gives you a simple relation. L value is 3, R value is 3. 3 by 3 is, of course, omega C. Together it is XL. They said R and inductive reactance. Inductive reactance means XL. XL equal to 3. Omega L equal to 3. R equal to 3 by 3 becomes 1. Tan phi equal to 1. Hence, theta equal to, we know that for what angle? Yes, tan phi is maximum. Tan phi is going to be 1, means phi equal to tan inverse 1. Tan inverse 1 gives you the phase angle is going to be 45 degree. Yes. An inductor 20 millihenry, capacitor 100 microfarad and a resistor 50 ohm are connected in series across a source. Means it is a LCR circuit. All the three have different values. 20 millihenry, 100 microfarad and 50 ohm are connected in series across a source of EMF V equal to Vm sine of omega t. The power loss in the circuit. Power loss, as I said in my last class, it is a product of VRMS, IRMS and a cos phi. Let me write it mathematically. It is VRMS is 10. It is Vm. Actually, you have to divide it by root 2, and it is omega t. Omega is 314. I need to write the formula cos phi. Phi is R upon Z. You have all the three people. You have L, you have C, you have R. We need to calculate XL, XC, then finally go for a formula, power loss formula. Let me address the first one. I take the equation granted. Standard equation I compare. I got V naught equal to 10, omega equal to 314. So next step, of course, a very simple mathematics. Do remember this formula. Power is given by RMS, VRMS, IRMS, root mean square value of voltage, root mean square value of a current, and a cos phi. Cos phi is called power factor, but here you have to talk about the phase angle. Phi is given by R by Z. Z happens to be the impedance. And this formula VRMS becomes VRMS square, Z becomes Z square, it is R. So hence it is VRMS square upon Z into R. The same formula VRMS is V0 upon root 2, Z as it is there. Let me go to the next mathematics. Now this impedance separately we know. Impedance is the total opposition offered by the circuit. Resistance, inductance and a capacitance. The formula looks in this way. R square plus omega L minus 1 upon omega C. Mathematically R is 500. It becomes 50 square means 2500. So simplification of omega L, if substitute 314 into 20 millihenry, everything 314 into 20, it is actually milli means minus 3, it becomes 0.3. 20 into 0.3 is almost close to 6, and 100 into minus 6, it is minus 3. Minus 3, of course, you have omega. So when you multiply, it is almost small. Simplification gives you 25.56, the difference between these two people. When you square it, 25 square is roughly 625. 2500 plus 625 is roughly 3000. Root of 3000 is close to, it is 56.15. We take it as 15.6 ohms. It is the total opposition offered by the circuit. Now formula is RMS. I know IRMS is very simple mathematics. You have a IRMS is given by VRMS divided by the total opposition. The formula is well taken care. It is VRMS upon the total opposition. See here the formula, or I can reproduce it once again. The same formula. It is, this formula is replaced. IRMS is replaced VRMS upon Z. So I can go with RMS upon Z. So RMS is, everything is 10 upon root 2. Then impedance is 56. Simplify it, you will end up with 100. Root 2 becomes 2. 56 again 3136 as it is. The answer is under root 316. You keep as it is, nothing wrong. Finally you'll get this answer 3136 into 50. Simplify 50. You have 100 3 zeros. There are 3 zeros, both will celebrate. Plus 3 minus 3, it is 1 upon 2.2 into 3.16. 3.16 means 3.1. 2 into 3.12, something like, will get close to 6.28. 1 upon 6.28 gives you roughly 0.8 watt. Meaningful. Let me have it again. Such questions appear. It's related to our voltage related concept. Yes. The potential difference across the resistance, capacitance and inductance are 80, 40 and 100. Means voltage across resistance 80, voltage across capacitance 40, voltage across, of course, inductance 100. You need to write it as VR, VC, VL equal to 80, 40, 100 respectively in energy. The power factor of this circuit. What is power factor? We discussed cos phi equal to R by Z. You need what is a Z. Look at this meaningful question. And finally, we'll have a simple analysis. Power factor is given by R by Z. Now multiply I and multiply and divide by the relation I by I. It becomes, it looks like V voltage across a resistor. It looks like total circuit formula. You have 80 I XL minus XC whole square. Then you have analysis. Go on substituting the values. What is XL? You make it IXL. IXL. The things remains as it is. You have taken I and it comes out of the see here, this I is inside. Once it comes inside, it becomes IXL minus IXC. You need to, instead of going for XC and XL, you need to directly make in terms of voltage. This is voltage across an inductor. This is voltage across a capacitor. 100 minus 40 becomes 60. 60 square plus 80 square. The simple relations are very simple. And it gives you very simple next mathematics. 80 upon 60 plus 80 square. 80 upon, both will celebrate because both have a simple numbers. You have root becomes 100 and 0.8. So finally, yes. Interesting and a lengthy. Okay. Figure shows a circuit that contains 3 identical resistors with resistance R equal to 9 ohm each, 2 identical inductors and with inductance 2 millihenry each, and an ideal battery with EMF 18 volt. The current I through the battery just after switch closed is. What will be the current in the circuit? Look, you have 3 resistors R, each value of 9 ohm. You have inductor LL whose value is 2 millihenry. What is the EMF here? 18 volt. And next, capacitance. Nothing they have mentioned capacitance value. So of course there is a C is a capacitor. How to address it? We know that whenever a DC source, it is a DC source now, it is not a AC source. Whenever a DC source is connected to circuit, when this switch is closed, the inductor will behave as open circuit, that is not closed. The circuit, it breaks the circuit here, and similarly it breaks the circuit here. Of course, the capacitor allows the current to flow through it very slowly. It opposes, means its opposition is less. So inductor totally opposes in the sense it will not allow the current to flow. Let me address it very systematically. At time t equal to 0, when the switch is closed, I switch the closed. Inductor in the circuit provides very high resistance because inductor is going to behave as open switch. It will not allow current to flow in this path. This path is called S block. Well, capacitor starts charging with maximum current with low resistance. There is a flow of current in this. So there is a flow of current here. There is no flow of current here. There is no flow of, therefore there is a flow of current. No flow of current. It acts as open. Here also no current. Of course, current flows here through the capacitor and directly again. It starts here, no flow current. Current flows here in this way, but there is no flow in this path. So let me make it a small diagram, the equivalent circuit diagram, how the circuit looks. When inductor is behaving as open switch, It acts as open switch. That's why there is no contact. There is no contact. The current starts here, it flows here, again the current flows here, and it goes. Capacitor will allow the current. That's why these two are joined. The capacitor means there is a flow of current. Low opposition, it's called as current, again come back to the circuit. So when at time t equals 0, when switch is closed, inductor acts as open circuit, capacitor allows the current to flow. Hence finally the mathematics becomes very simple. This is a final simplified circuit diagram. Of this whole circuit diagram reduces to, this is 1, because this whole, there is no current means as if there is no fun in including in the circuit, remove it. I have one circuit, again you remove this part, it becomes a resistor RC circuit. This resistance, capacitance or opposition offered by capacitor is very low. I can treat it as negligible resistance in comparison to R. Hence this becomes R plus R. Looks like two resistors in parallel combination. So parallel combination is R square upon R plus R, it is 2R. So I hope you know series combination means R plus R, the effective resistance. Parallel combination means product divided by sum. Product means R into R, R square divided by R plus R, 2R. R square upon 2R gives you R by 2, the simple logic. So finally, what is a current? By Ohm's law, current in the circuit is given by EMF divided by the equivalent resistance. The equivalent resistance is R square by 2R, so it becomes R by 2. It becomes 2 times EMF upon R. R value we know it is a 9 ohm. Both celebrates. Finally, we'll get 4 ampere. Asked a simple analysis. Which of the following combinations, there are 4 combinations, RCL means RLC, RLC, RLC values, there are 4 values, be selected for better tuning of an LCR circuit used for communication. For better tuning, I discussed quality factor. I hope you remember quality factor is given by, yes, XL upon R or XC upon R or your frequency by frequency. It's called resonant frequency due to bandwidth concept. Let me go with these, all the 4 combination. I have RLC, 20, 1.5, 35, 25, something like. For better tuning, peak of current, that is I equal to V upon Z. Z becomes, impedance becomes very low. When Z becomes very low, of course, the current becomes very sharp and Q becomes very high, as I said. Peak of the current growth must be sharp. This is ensured by a high value of quality factor Q. So what is quality factor? Quality factor is a ratio of course, you can go with this formula also. Quality factor is also given by 1 upon R under root L by C. So this is also a kind of a formula you can cross check. Sir, from where we got your formula? You remember you have a beautiful formula. So that is XC equal to XL concept and oscillation concept. The quality factor left hand side, you write some formula that is in terms of bandwidth and frequency, resonance frequency formula. You'll get this factor. Quality factor can also be written as 1 upon R under root LC. Quality factor can be written as 1 upon R under root LC. All the 3 values are given. When there are 2 values, it's good. What is the mathematics? So go on doing the simple mathematics. But the best idea is when you look at this formula, L by C combination, you have L and C combination. C value is, of course, 35, 45. From the given options, the highest value of Q is associated with R equal to 15 because among the 4 choices, 20, 25, 15, and 25, R value is the least. You go for the first preference here. Next, go for the combination 3.5 by 30. 3.5 by 30 gives you very close to almost 1.2, roughly close to 1.2. Means 1.2 into 10 raised to minus 1, it becomes close to 0.12. Root of 0.12, you can make it as 12 into 10 raised to minus 1. Root of 12 is almost, you have an answer close to 3.5. 3.5 by 5 is 1 upon 0.5. So finally, what we need to say, quality factor is large for this combination. The combination is resistance is less, too less, and you can take the other combinations. And see, for all other combinations, you can have 1.535, 1.545. There are 2 values, opposite values, and you have 2.545. When you do all the mathematics, you'll come to know that the quality factor, of course, takes care of R also. And do remember, in one of my earlier discussions, I had said the sharpness of a curve depends upon the R value. And this is very simple. A transformer having efficiency 90% is working on 200 volt and 3 kilowatt power supply. If the current in the secondary coil is 6 ampere, the voltage across secondary coil and the current in the primary coil respectively are. Do remember, the question is simple. The efficiency of the transformer is 90%, working on a 200 volt and 3 kW power supply. If the current in the secondary means IS, the voltage across secondary coil and the current in the primary coil. You need to calculate what is the voltage in secondary and the current in the primary. This is called primary voltage. So there are two things. Again, primary voltage is 200 volt, primary current is 6 ampere. The power is 3 kilowatt, 90% efficiency. Initial power equal to final power. We know the concept that there is no power loss, thinking that the transformer is ideal in nature, but here it is a 90%. So let me use this formula. So as efficiency is 90%, then final power is going to be initial power equal to 3000. Final power is going to be 3000 into 90 upon 100. It comes out to be 2700 watt. Means I cannot take this transformer as an ideal transformer. What is an ideal? Initial power equal to final power. Since it is efficiency is 90%, not 100%. So I need to calculate final power. Then let me go to the next formula. You have this formula. Given value is initial current, that is the primary current 6 ampere, and voltage is 200 volt. The formula. So you have this rule. V1 I1 equal to initial power equal to this, final power equal to 2700 watt. By using these formulas, you have initial voltage 200, you need a current I1. I1 you can easily calculate. You need to calculate V2 equal to I2 already given. Of course, once you calculate, you will get the simple analysis. Yes, this is your formula. That Vt equal to 450, 2700 by 6. Why 6? Because the current in the secondary is 6 ampere. There is a small error, a printing error. It should be taken as I2 equal to 6 ampere. So finally get I1 equal to 15. Cross check.